we could take the same exact curve and we could break it up into smaller rectangles. So let's say we broke it up, I don't know, here, here, and here, but then we increase the density. Let's do this instead. So we end up with this. Now there are more little edges that are over, but they tend to be smaller. So it looks like as we increase the number of sections, what happens to the estimate? It looks like if there are more rectangles, accuracy of estimate improved. What? It does seem tedious. It does seem tedious. Now, are we going to sit there and write out the area for each individual rectangle?
I hope not.
No, we're not going to write the area for each individual rectangle. We're going to come up with an expression for the sum of all of them, and then we're going to evaluate that expression. That expression, exactly. We're going to increase the number. Exactly. Okay. Like all of them, right? So we're going to write an expression for the combined area of all the rectangles for a certain number of rectangles, n of them, and what are we going to do to this expression? We're going to see what happens to this expression as what happens.
Goes to infinity.
The number of rectangles, n, goes to infinity. We're going to evaluate a limit. The limit as n goes to infinity. But what we need to do is write an expression for what is the estimated area of this curve broken up into how many rectangles? N of them, right? So let's say we did break it up into n rectangles. Like this, okay? That dot represents, there's a lot of them, okay? If this goes from 0 to 1, can you tell me what the width of each of these rectangles is? What? 1 over n, yeah, exactly. You're totally right. Each width is 1 over n. How do you know that? There's n rectangles, and it goes from 0 to 1. Where does this come from? What happens if it was, let's just generalize this a little bit. What happens if it was 0 to 8? What would the width be? 8 over n. What happens if it was 6 to 12? What would the width be? 6 over n. What happens if it was pi and 4? What would the width be? 4 minus pi over n. So where does the numerator come from? The base, exactly, the width of the base, exactly. So that is equal to, if this is b and this is a, this is b minus a all over n. So again, the reason I'm showing you this is because it doesn't matter if it goes from 0 to 1, 0 to 2. No, our method, whatever we're using right now, we can take care of it going from 0 to anything, 2 to a to b, with the numerator of that fraction. Okay, that's the base of each rectangle. How do you find the area of a rectangle? You multiply the base times the height. Okay, so this is where we have to be kind of a little careful here. Let's use a rectangle like this. So if I wanted to write the area of that first rectangle, that's the first rectangle right there. What's the base of that rectangle? 1 over n. And what's the height of that rectangle? 1 over n squared. How do you know it's 1 over n squared? This point right here is the height. Do you see that point right there, everybody? That point? What's the height of that point? How high up is that? Well, that's the x value of that point evaluated at the function, right? The function is what? Y equals x squared. Exactly. What's the x value for this second mark right there? What's the x value right there? 2 times 1 over n. It's the second one, right? So that's the x value. So what's the coordinate right here going to be? That second height right there. 2 over n quantity what? Squared. Exactly. So we're going to write this rectangle. So the second one is going to be 1 over n times what? 2 over n squared. Are we okay with that? Okay. You can see a pattern, hopefully. What's that third rectangle going to be right there? 1 over n times what? 3 over n squared. It's the function acted upon the x value, right?
This equation only works for the case of x squared.
Well, if we change f of x, it just changes the output. Yeah. So right here, let's do this last one right here. Again, what's the width of this one? 1 over n. What's the height of this one? What's another way to write that? N over n squared. What's this one right here, the second to last one? What's the area of this one going to be? 1 over n, what is it? N minus 1 over n squared. Does everybody see that right there, how we figured that out? So if we're going to make an estimate of these all together, we have to add them all up. Are we okay with this idea? We're going to add them all up. So if we add them all up, we end up with, just so you can see this here, our estimate is going to be something like the first one plus the second one. I'll do a third one. That's fine. Plus, what's the second to last one? 1 over n times n minus 1. Not 2. That was 1 over n squared. Let's make this a little smaller. Plus what? 1 over n times. It helps to keep it in n over n form. Keep it like this. I'll put a star there because you need to see how it ends. Just believe me on that for now, okay? What can we factor out of this? What's the easiest thing we can factor out? Yeah, so you have 1 over n times 1 over n squared plus 2 over n squared plus what? 3 over n squared plus n minus 1. You're going to do a lot of dots squared plus n over n squared. Are we okay with that so far? What can I further factor out of each of these? You can't factor out a squared. That's an action. What's in each of these terms? 1 over n is, you can get better than that. 1 over n squared is in each of them, because that's 1 squared over n squared, 2 squared over n squared, 3 squared over n squared, right? So what does this become? 1 over n to the what power? Cubed times what? Squared plus 2 squared plus what? Plus n minus 1 squared plus n squared. Okay, so what are we now looking at? We're looking at this. We're looking at the limit as n goes to infinity of 1 over n cubed times this, right? Are we okay so far? Is everybody okay with the fact that the dot part is the new part of it? So this right here is what we need to talk about right here. You've seen that before. There's a famous story. I forget which mathematician it is, and one of you could look it up and find it. But famous mathematician, when he was very young, sitting in a math class, like 7 or 8 years old, and the class was giving the teacher a hard time. So the teacher said, "Okay, find me the sum of the first 100 squares or something." Was it Gauss? First 100 squares. And the teacher's assuming 1 squared plus 2, add them all up. He's like 15 seconds later, he's like, "I have the answer." So the question is, we need to come up for an explicit formula for this. What does an explicit formula mean? You don't need the term before it, exactly. Or you don't need all of the other terms. You can just say, what is the sum of the first n squared? That's the question here. What is the sum of the first n squares? And these are integers. What's the sum of the first n squares? Have you seen something like this before? Some of you have seen this before in other math classes. Sometimes you see this in grades. It's just it's a neat observation. And we don't prove this in this class, but it's something we use. No one's seen this before? This is equal to this. So let's actually write that out. So now it says the limit as n goes to infinity of 1 over n cubed times what? What do we write instead? Times plus 1 times 2n plus 1 all over 6. Yes, that is correct. This is only specific to x squared. Correct. So at this point, we are now back to the land that you should be comfortable with. You should be comfortable with this. We've done things like this before. How do you attack a limit like this? What would you need to do? No L'Hopital's. This is not indeterminate. What do you do first whenever you see something like this? No! Simplify! You always look to simplify. You always look to simplify. So what can we do to this? What? Multiply them together. So you're going to get the limit as n goes to infinity. It's going to be 6n cubed on the bottom, right? You're going to have n squared plus n times 2n plus 1. So what does that equal? That's the limit as n goes to infinity of what? Of what?
2n cubed.
2n cubed plus n squared plus 2n squared plus n all over 6n cubed. So that's the limit as n goes to infinity of what? 2n cubed plus 3n squared plus n all over 6n cubed. What does that equal? 1 over 3. Why does that equal 1 over 3? This is the most basic type of limit evaluation, except it's not directly plugging in. So the first thing you check, you can't plug in infinity. But how do you know that's true? What's the power of the top? What's the power of the bottom? The powers are therefore equal. Do you remember this from like week 1, like
6.
day 3, I think? It's 2 over 6, which is...
1 over 30.
The way you look at this, the proper way, if you want the side way of doing this, is it's the limit as n goes to infinity of 2n cubed over n cubed plus 3n squared over n cubed plus n over n cubed all over 6n cubed over n cubed. What did I do? I just divided everything by n cubed. What happens? This goes away. That's gone. That goes away. This is gone, turns into n squared, and this goes away. So what are you left with? You're left with the limit as n goes to infinity of 2 plus 3 over n plus 1 over n squared all over 6. As n goes to infinity, what does this go to? What does this go to? So that's 2 over 6, which is what? 1/3. So what did we just prove? We just proved the area under the curve is 1/3.
Approximately.
No, it is 1/3.
It is?
That's what the limit tells us. The limit tells us as we get infinitely close, what are we going to? We're getting infinitely close to 1/3. So what is the actual volume? What is the area under this curve? 1/3. Exactly. The limit. Okay. So what does this mean? What does it mean? So what is n representing? The number, not triangles, rectangles, right? So the limit as n goes to infinity means what are we doing? Taking more and more what? Yeah. We're making more what? We're making more cuts. Making more cuts. Okay. You don't focus on this for a second here, but what was f of the value? What did that tell us? The height. This right here is the height. And what's this right here? That's the width, right? Delta x is going to be the width of each of these pieces. Xi is which x value between the a and the b value. So when we did x squared here, and I'll draw this a little better than that. When we drew x squared from 0 to 1, we made lots of cuts right here, all the way up to the last one. The first cut you can call x sub 1. The second cut you can call the value x sub 2, and then what? X sub 3 and x sub all the way up to what? X sub n. That's the x value you're going to. What was the value in this? If this was y equals x squared, and you're going from 0 to 1, what was the value of x1? 1 over n. What was the value of x2? 2 times 1 over n, right? Are we okay with it? And it keeps on going. Now, so that's what it means. X sub I just means you go through each one. What is I going from? 1 all the way up to n. That's what we did. We went from 1 to n. Okay, what's the last little bit there that seems strange? Not the sigma means add them all up. That's where the pluses come from. You know where pluses. We need pluses. What's the one last thing that you have never seen before? What's that thing called? Okay, the sigma means what? Add it all up. Add it all up. So what's the last symbol on there we haven't explained? The asterisk. This thing right here. This thing right here. What does that mean? Here's what it means. When we took our limit here, we used the right hand side of each of these rectangles. Could we have used the left-hand side? We can. I have a question for you. When we were doing this estimate, was this estimate an overestimate or an underestimate? Why was it an overestimate? They hang over, they go above it, right? The left endpoints, if we use the left endpoints, we would break up to the same intervals. We would have these breakups. Right here we go 1, 2, 3, 4, 5, all the way up to n. But then we'd use the left-hand one instead. So we would draw this rectangle, and then we would draw this rectangle, and we would have, sorry, I got to keep going here. We do this rectangle and this rectangle. If you add all these up, is this still an estimate? The first rectangle actually has no height. The first rectangle is right there. See it? Has no height. Is that still an estimate?
Yeah.
Yes. Is it an underestimate or an overestimate? Underestimate. But as we take more and more rectangles, what happens to the estimate? It gets more accurate. So is it going to go to the same limit? Yes. So here's left hand. If it's concave up in left hand, it'll be an underestimate. If it's concave up in right hand, it'll be an overestimate. So we use the left endpoints and we use the right endpoints. Could we use the middle? Could we use the middle value? Absolutely. What does the middle value look like? You could take, here's x squared. And let's break it up again. Let's say it's here, here. I'll just make it bigger so I can draw this. Instead of taking, so this is x1, this is x2, x3. So instead of taking the right hand or the left hand, I'm going to take the middle point. So I'm going to say the height is here. Sorry, the height is here. So you go up to here. Here's our first rectangle, right there. Then we go to here. Here's our second rectangle. We go to here, which is right there. Here's our second rectangle. Does everybody see these rectangles? Are these conclusively under or overestimates?
Nope.
Not necessarily, right? This generally would be a little bit more accurate, but it's not going to be exact, so you have to take the limit, right? So we've taken left hand, we can do right hand, we can do an average. What happens, though, for each of these limits? Do these limits go to different things?
They should.
No, they go to the same thing. They do go to the same thing. As you break these up into more and more, they get infinitely close to the actual limit. So does it really matter where you take the sample point in between each two x values? Could you take different sample points? Do you have to always take the middle or always take the right hand?
No.
Could you do left, right, middle, left, right, middle?
Could if you wanted.
Why? Yeah, exactly. Why does it not matter?
It's going to go to the same limit, I think.
Why?
And the area is not changing.
The area's not changing, but I have a question for you. Why? As you break them up into more and more rectangles, what happens?
They get infinitely thin.
They get infinitely thin, right? They get infinitely thin. So if you're always taking your sample point between two things and they get infinitely close together, you're going to approach the same limit. So what this means right here, this xi star means any x value between x sub I minus 1 and x sub I. That means any x value between. So if you want the height of your rectangle, you can take any value between those two x values. It doesn't matter because as you take more and more cuts, as you make more and more cuts, what happens to the boundary? What happens to the width of each of these rectangles? Really, 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 really small, right? So if you're only taking values between it, does it matter if you take the right or the left?
Nope.
Not in the end. Might it take a little bit longer, but you don't really care how long it takes because you're going straight to looking at as n goes to infinity. Are we looking for the relative accuracy as you increase the value of n? No. You're looking for what is the target as n goes to infinity. Okay, so going back to this process here, what was the only truly new thing that I introduced here? No, well, the dot 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 was the new notation. What was the next true mathematical fact that you hadn't seen before? The formula for the sum of squares. That's the only new thing I've shown you so far. But that only works with squares. Keep that in mind. Let's break this up into 5 sections. There's 5 of them, right? If we want to make an overestimate, should we take a right endpoint or a left endpoint? Let's see here. Let's do right. If we take right, so here are our rectangles. Here they are. Yay. Okay, there they are. So how do you find the area of rectangles? Base times height. What does it look like the area of the first rectangle is? 6. And assuming we're only going to half decimals here, this one looks like it's a base of 2, which all of them are, right? What's the height of that second rectangle? What's it look like? 4.5. So what's the area going to be? 9. And then it's going to be 5.5, so it's going to be 11. And then let's say it's 6.5, so it's going to be 13. And the next one's going to be 14. So what's our overestimate going to be? 15 plus 24 plus 14. 39 plus 14 is 53. Are we okay so far? There's our overestimate. How would we make an underestimate? Use the left endpoint, exactly. So let's get a better picture here. Let's do that again. So if we take this picture again.
So
that's our
we're just kind
overestimate.
of we're just kind of guessing by estimation.
Yeah, exactly.
Okay.
Yeah, you have to be comfortable with that. You will definitely be asked to estimate something on the AP exam. I'd be
Okay,
surprised if you were not. Okay, so if we do the same breakups here, and we want to do an underestimate, let's take the left endpoint. So what's our first rectangle? First rectangle is going to be here. What's our next one going to be? Here. Next one's going to be there. There. And what's our last rectangle? It actually looks like our last, it actually has a height because look, it has a height there, see? So what does it look like the area of our first rectangle is? 2. And then what is it? 6. And then what is it? 11. And then what? 13. And then? Looks like it's 6.5, so... We sure about that? Oh, we did something that's not quite right. That one's 6, right? What's this one going to be? 9, 11, and then what? 13. So what's the area here? It's going to be 8 plus 20 plus 13 is 28 plus 13, which is 41. Is that right? 41. So what's the tendency if we have an overestimate and an underestimate? If you want to get a better estimate, what might you do? Just... If you had an overestimate and an underestimate, what might you do to try to get an average them, right? So maybe our average is, this is just a side note. It's going to be 41 plus 53 over 2 is 94 over 2, which is 47. So it looks like maybe a better estimate would be 47. Is averaging always going to work? Not always, but do you think that's a better estimate? I think it's a better estimate. It's over and under. We're somewhere in the middle. The middle is going to be closer. Find new estimates using 10 rectangles. So let's actually do this again. Let's do one of them. If it asked you for an estimate based on an average, sure. But could your to answer this question, it's specifically asking what's the overestimate and what's your underestimate. Over was 53, our under was 47. So now it says break it up into 2. Also, we were estimating these as half heights. I mean, can you be a little more accurate with your estimation? Absolutely. Let's do one more of these. So we break it up into 10 of them. Yay. Let's do right endpoints. That one. There's this one. It's exciting stuff, isn't it? And then we have here. And then we have here, 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 and here. So if we do that all out, we have 10 more things to add up together. Let's do that. We don't need this one on record.
Yeah.
Is this pretty similar?
It's a computer algebra system.
A computer.
Just say calculator.
Express the area under the curve y equals x to the fifth from 0 to 2 as a limit. Is this pretty similar to what you've already done? Absolutely. Set as much of this up as you possibly can. Put your calculator down. I don't care about your answers that your calculator is giving you using the fin function on your calculator. I would like you to write me as much of you can. At this point in your calculus career, what's the problem?
We don't know how to get to that equation.
What equation? Can you give me a complete sentence? Like if you're going to ask somebody for something, what would you be asking for?
The area of the square.
Okay, let's go back up here. In green, I wrote.
Yeah, I don't know how to say it.
That equation. And someone versus n squared.
Okay, that was the first one, so what do we want now? What? Yeah, exactly. What is the sum of the first n fifths?
Is there a different way to say it?
Yeah, well, there's n cubes. The first n quartix. I think it's n quintix. Quintix. I think it's quintix. Quintix. I think. Now the question is, am I going to have you memorize the squares, sum of the first n squares? Absolutely. What about this? 1 plus 2 plus 3 plus all the way up to n. Are you going to have to memorize that? Absolutely. Nothing to do with factorial. Nope. You will have to memorize this and this all the way up to the sum of the first n squares. Am I going to have you memorize the cubic? No. The fourth one? No. The fifth one? No. They get progressively worse. They're not totally worse, but they're just big. They get bigger, and they're not something I want you to memorize. Will you have to use them? Will I give something like that to you if I expect you to do this by hand? Absolutely. What power are you hoping this will come out to be? What power do you hope this will use?
6.
Sixth. Why?
The other one is 6.
Yeah. If this wasn't 6, will this ever go to a static number?
No.
No, either like infinitely big or infinitely small. You need that to go to something involving the 6th power in the numerator. Exactly. Okay, let's pause this here.